Okay, so get this. We're diving into something pretty wild today. Like we're talking about the idea of breeding super soldiers.
Super soldiers.
Yeah, I know, right? Sounds like we're stepping into a sci-fi movie or something. But stick with me on this one because there's actual science behind this whole thing.
Okay.
I'm intrigued.
All right, so we're talking about this thing called genomic selection.
Genomic selection.
Yeah, it's this technique that's actually being used right now to breed animals with like very specific traits.
Oh, wow. I mean, that's pretty amazing when you think about it. Like they're breeding cows that produce way more milk or like racehorses that are insanely fast.
Exactly. How do they even do that?
Well, it all comes down to their DNA.
Yeah.
You know, scientists analyze it and they can pinpoint certain genes that are linked to those, desirable traits.
Huh, so like by understanding the genetic code, they can actually kind of engineer the outcome?
Pretty much so. Today's deep dive is all about taking those principles, the ones they use for animals, and hypothetically applying them to humans.
To humans? Wait, are we talking about like designer babies now, or?
Not exact. I mean, we'll get into the ethics of it all later, but for now, let's just focus on the science. Okay?
Yeah.
So specifically, we're focusing on soldiers, and we'll use the Army Physical Fitness Test, the APFT, as our benchmark.
Oh yeah, the APFT, right? Push-ups, sit-ups, the 2-mile run.
That's the one. So what if we can use this genomic selection thing to actually breed soldiers who can just ace this test every single time?
Okay, that's a pretty wild thought, but how would we even begin to do that?
Well, to get started, we need to grasp the basics of genetics, right? So think of our DNA like this crazy detailed instruction manual for building a human being.
Okay, I'm with you.
And within this manual, there are these tiny variations called SNPs, single nucleotide polymorphisms.
SNPs, that's a mouthful.
I know, right? But they're basically what make each of us unique.
So like those tiny differences in our DNA that make me and you, you?
Exactly. And get this, there are millions of these SNPs scattered throughout the human genome.
Millions.
Wow, it's mind-blowing, right? And you can think of these SNPs like tiny little switches that can actually tweak how our bodies function.
Including things like our physical abilities.
Bingo.
Okay, so SNPs are like these little genetic tweaks that can affect things like muscle strength or how long you can run without getting tired.
You got it. But here's the million-dollar question. How do we connect these SNPs to something as complex as acing the APFT?
Yeah, that's a good question because the APFT isn't just about one single trait, right? It's a combination of strength, speed, and endurance.
True. So this is where things get really interesting. We need to start by analyzing the DNA of soldiers who already score really well on the APFT, like the top performers.
Looking for those SNPs that they all share.
Precisely. It's like a detective story, trying to find those hidden clues in their DNA that give them that physical edge.
I like that, a genetic detective story.
Right. And this is where a concept called linkage disequilibrium, LD, comes into play.
Linkage disequilibrium.
Yeah, it's a mouthful. But basically it means that SNPs that are located close together on a chromosome, they tend to be inherited as a package deal.
So if we find a bunch of SNPs that frequently pop up in these super fit soldiers, we can kind of guess that those SNPs are linked to genes that contribute to their, APFT domination.
You got it. It's like having a map that guides us to the genes responsible for those amazing physical traits.
Wow, so it's not just about finding the right genes, but also understanding how they're all connected.
Exactly.
This is blowing my mind.
Right. So we've identified these potential genetic markers for APFT success. But now what? How do we actually breed soldiers who inherit those traits?
And that's got to be the toughest part, right?
Well, this is where we dive into the world of statistical models.
Statistical models.
Yeah, these are like super sophisticated algorithms with fancy names like BayesA and BayesB.
Hey, say BayesB. Are we talking about robots now?
No. These are just mathematical formulas, essentially.
Sure.
And they help us predict the likelihood of someone's offspring inheriting those high-performing SNPs.
Hold on. So we're not just looking for the right genes, but we're trying to predict how likely those genes are to be passed down to their kids.
Exactly. It's like peering into a crystal ball and seeing the future of someone's physical potential just by looking at their DNA.
That's wild. I mean, if this is even possible, the implications are huge.
Right. So just to recap, in this theoretical program, we'd analyze the DNA of our top soldiers, find those key SNPs, and then use these statistical models to predict the APFT potential of their kids.
And then over many generations, we'd selectively breed the individuals with the highest predicted scores.
Yeah, in theory, that's how it could work. But remember, we're talking about a purely hypothetical scenario here. We're exploring the science, not saying we should actually do this.
Okay, good, because that would open up a whole other can of worms, ethically speaking.
Definitely, but it's a conversation for another time.
All right, I'm all ears when you're ready to dive into that.
Don't worry, we'll get there.
Looking forward to it. Yeah, and it's important to remember, this whole super soldier thing, it's all theoretical. But in the real world, we're already seeing this genomic selection stuff play out, with like animal breeding.
Oh, yeah, for sure. I mean, you mentioned those super cows and like the crazy fast racehorses.
Exactly, and the results have been incredible.
I'm curious, though, like how has this technology actually changed things in animal breeding? Like what did they do before?
Well, for years, breeders, they relied on traditional methods, like basically looking at an animal's appearance and its family history to try and predict its potential.
So they were kind of just winging it.
Pretty much. It's like trying to bake a cake without a recipe, just by looking at a picture of one.
You might get something that looks like a cake.
Right, but it might taste awful.
Exactly. So this genomic selection thing, it's like having the entire cookbook.
Ugh.
The detailed genetic blueprint right in front of you.
Exactly. It lets breeders make much more informed decisions about which animals to breed, and it speeds up the whole process of improving those desired traits.
So are you saying that breeders can now, like, fast forward evolution, like skip ahead a few generations and get to the super cows and the champion racehorses way quicker?
That's a great way to put it. Take the dairy industry, for example.
All right.
With genomic selection, they can analyze a calf's DNA and predict how much milk it will produce as an adult.
Wow, and they could do that even before it's fully grown.
Even before it's weaned.
That's incredible. So
Yeah.
no more waiting years to see if a cow lives up to its potential.
Exactly. And it's not just about milk yield either. They're using genomic selection to target all sorts of traits, disease resistance, meat quality, you name it.
So it's like they're customizing these animals to have the exact traits they want.
In a way, yeah. And it's been super successful in breeding faster racehorses, too.
Okay, now we're talking my language. Speed, agility, stamina.
Yeah.
That's what wins races. So how do they pinpoint those equine superstars?
Well, they analyze the DNA of horses with proven track records, the ones that are already winning.
Right.
And by doing that, they can identify specific genes linked to those winning traits.
So they're looking for the genetic recipe for success.
Exactly. And then they can use this information to hand pick promising young horses for breeding.
So they're basically creating a dynasty of winning racehorses, all thanks to DNA.
Pretty much. It's fascinating stuff.
Right.
But let's bring it back to our, hypothetical super soldier program.
Right.
We've established that, genomic selection could, in theory, be used to breed soldiers who excel in the APFT. But how do we even measure the accuracy of such a program?
Yeah, how do we know it's actually working?
That's where validation comes in. Remember how we talked about dividing the population into training and validation groups?
Yeah, we use the training group's data to build the program, right? To find those key SNPs and fine-tune those statistical models.
Precisely. We're essentially using the training group to teach the program what to look for.
Okay.
Then we test it on the validation group.
Gotcha.
We predict their APFT scores based only on their DNA, and then we compare those predictions to their actual scores on the test.
So it's like a real-world test for the program. The closer the predicted scores are to the actual scores, the more confident we can be that it's accurate.
Exactly. And scientists have all sorts of ways to measure this accuracy, from simple correlation coefficients to more complex statistical techniques.
So they've got it down to a science.
Pretty much.
Yeah.
They even have ways to adjust for the influence of parents, to make sure that the program is really isolating the genetic factors that are contributing to those top APFT scores.
It's like they're filtering out the noise to get to the pure genetic signal.
Exactly.
So it's a multi-step process. It's not just about finding the right genes, but also predicting how likely they are to show up in future generations, and then testing those predictions to make sure the program is on target.
You got it. But even with the most sophisticated programs, we have to remember that humans are way more complex than cows or horses.
Oh yeah, for sure. I mean, we can't forget about all those other factors that play a role in shaping a soldier's abilities. Things like training nutrition, even their mental toughness.
Absolutely. While genomic selection might offer valuable insights into someone's genetic potential, we can't just say genes equal destiny.
It's like that age-old debate, nature versus nurture.
Right, exactly. Genetics might provide the raw materials, but the environment shapes how those materials are ultimately used.
And with humans, there's so much more to the equation than just our genes.
Absolutely. The more we explore this genomic selection stuff, the more we realize just how complex the human genome really is. It's a fascinating field with so much more to discover.
This has been a wild ride. Like, we've gone from tweaking the DNA of cows and racehorses to talking about creating super soldiers.
It really makes you think.
Yes, and it brings up this big question. Even if we could perfectly predict a soldier's physical potential just from their genes, should we even do that?
That's the million-dollar question, right? It makes us think about what human potential really means.
Yeah, like, are we just a product of our genes, or is there something more at play? Something that shapes our abilities and makes us who we are?
It goes back to that classic debate, nature versus nurture.
Exactly. Like, were those amazing athletes or brilliant scientists always destined for greatness just because of their genes? Or did their environment, their experiences play a role too?
And when we start talking about choosing people for specific roles based solely on their genes, things get ethically complicated.
Yeah, it's like, are we taking away their choices, their freedom to pursue their passions by basically deciding your future for them?
It's a slippery slope, you
Yeah.
know? Do we really want to live in a world where our DNA dictates our careers, our potential, even our value as a person?
That sounds a little too close to some dystopian sci-fi movie for me.
It raises some serious questions about individual freedom and the potential for discrimination based on genes.
Right, like if we put so much emphasis on certain genetic markers, what happens to the people who don't have them? Are they considered less valuable?
That's a lot to consider.
It definitely is. This deep dive hasn't given us all the answers, but it's definitely made us think about some important questions.
We've explored the science behind genomic selection, this technology that's already changing how we breed animals, and we've thought about what could happen if we applied it to humans, especially when it comes to creating soldiers with enhanced abilities.
We've learned about these tiny things called SNPs, these little variations in our DNA that can affect everything from how much milk a cow produces to how fast a racehorse can run.
And those statistical models that let us predict the chances of those traits being passed down to the next generation, it's amazing.
It is. But I think the biggest takeaway from this deep dive is realizing that even with all our advances in genetics, we can't forget about the interplay between nature and nurture.
Your genes might give us the blueprint, but it's our experiences, our environment, and our choices that shape who we become.
So as we wrap up this exploration of genomic selection, we're left with this thought. The ability to change the very building blocks of life comes with a huge responsibility.
It's a power that demands careful thought, open discussion, and a lot of humility.
And who knows, maybe the true super soldiers of the future won't be defined by their physical strength alone, but by their courage, their resilience, and their dedication to something greater than themselves.
That's a powerful thought.
Until next time, keep those brains buzzing.